Okay, in this video we are going to talk about the formation of planetary systems. We talked about our solar system and the planets in our solar system. We're going to talk about other planetary systems as well. And we want to get a basic idea of what we understand about how stars and their associated planetary systems form. We have had a general idea about how planetary systems probably form since the very early part of the 20th century, the 1920s or so. And the idea is we look at a solar system and everything is rotating in the same direction, with a few very small exceptions, some comets and asteroids and moons and wacky orbits, but everything goes around in the same direction and almost in the same horizontal plane, which suggests that whatever formed the solar system formed out of something rotating and all rotating in the same direction. And this simple observation gave rise to what was called the Nebular Hypothesis, that the solar system, our solar system, started out as a cloud of gas and dust that was pulled together by the force of gravity. And as it was pulled together by gravity, the amount of spin that it had gradually started to increase. I think we've talked about already in the course the idea of this law of conservation of angular momentum. Like an ice skater who pulls in her arms, spins faster and faster and faster because they're decreasing their moment of inertia and their angular speed increases to compensate for that. That law, conservation of angular momentum, we see in everyday life. It applies to an object gravitationally collapsing that will spin faster and faster and faster. And as it spins faster and faster and faster, it will also flatten out. Just like a piece of pizza dough that you throw up in the air and give some spin, flattens out. And so this increasing rotation and flattening explains the general shape of the solar system. As gravity pulls the center in denser and denser and denser, that gas in the center will get hotter and hotter and hotter until what you have is a dense ball of hydrogen gas being compressed by gravity, surrounded by this rotating disk of gas and dust. When that star in the middle, when that 2B star 2B in the middle starts to heat up, it will start to give off infrared light. And that object is called a protostar. A protostar is a star that is in the process of being born, but is not yet fusing hydrogen into helium. It is not hot and dense enough yet for that fusion process to occur. As gravity squeezes that protostar harder and harder and harder, and the heat in the core gets greater and greater and greater, it will eventually reach the point where it can fuse hydrogen into helium. And then you've got an honest-to-goodness star surrounded by this rotating disk now of dust and ice particles and gas that will clump together gradually into larger and larger chunks, and those larger and larger chunks become planets and moons and asteroids over time. So this picture of the formation, this model of the formation of the solar system has again been around for almost 100 years, maybe even a little bit longer. The question is, what evidence do we have that this is what really happens? I've said a few times already in this class that in astronomy, we don't get to just sit and watch something like the evolution of a star or the formation of a star system happen, because that process takes millions, hundreds of millions, maybe even a billion years, and we can't sit around for a million years and watch something happen. All we get is little snapshots of what is happening in space for the lifetime of humans. We've only had the ability to take pictures of space for barely 100 years. So what instead we have to do is assemble the snapshots we see out in space into a story that matches our models of what we think happens in some particular process. So how does that look? Well, do we see big clouds of cold gas that are being pulled together by gravity into denser and denser and denser clumps? Yes, here's a picture of the Hubble Space Telescope of a big cloud of gas and dust, so dense that it is opaque and blocking the light behind it. And here we see places where the gas is clumping together into a dense little opaque sphere. And that is exactly the kind of thing that we think happens when a solar system forms, that gravity clumps this gas together into a denser and denser and denser object. We see these dense clouds of hydrogen gas. This is not a place where there are no stars. This is a big black cloud of hydrogen that is opaque, that is blocking our view of the stars behind us. So we do see these dense collapsing clouds of gas. Here's another picture from the Hubble Space Telescope. We see these places, these very almost spherical black clouds of gas are called Bok, B-O-K globules, named after an astronomer whose last name was Bok. Again, we see these little, where is it, over, I can't reach, over there. We see some down here. We see some over here. We see these dense clouds of gas all over the place in our own galaxy. So we know that this happens. We know gravity can take a cloud of diffuse hydrogen gas and collapse it into a dense, opaque cloud of hydrogen gas. These are just more examples because they're cool to look at. Some of them very, very spherical, some of them very, very, very large. Again, blocking out the light of this diffuse nebula behind it as gravity pulls it in denser and denser and denser. We also notice that when we see often young stars, young hot blue O and B type stars, they are still surrounded by this gas or this nebulosity. So we see young stars in the process of sort of shedding this gas out of which they formed. When the star gets hot enough to start fusing hydrogen to helium, heats up to thousands of degrees on the surface, the solar wind begins to then blow this gas out of the system. So our solar system is not filled with diffuse hydrogen gas that blocks our view of the sun. We can't see this cloud of gas out of which our solar system is formed because the solar wind over the past 4 billion years has blown all that gas out into interstellar space. And so the nebulosity, this cloudiness out of which stars formed, is still there at the beginning, but it eventually gets sort of blown away. By the way, these are the Pleiades in the constellation of Taurus. You can see these in the winter to the right of Orion. So young stars look the way we would think young stars look if they formed in this cloud of hydrogen gas. And we see various places where it seems like there are young stars being born as we speak, or if they're 1,000 light years away, 1,000 years ago. We see stars forming in exactly the kind of situations that we expect to see stars forming. This is actually the Orion Nebula, just below Orion's belt and his sword. The sort of third star down is not a star, it's a gas cloud, and we can see brand new stars forming in this cloud of gas. The newly commissioned and launched and activated James Webb Space Telescope is going to be an incredible tool for studying the process of star formation. There are two pictures here of the same spot in the Carina Nebula. At the top, an image from the Hubble Space Telescope. At the bottom, an image from the James Webb. You can see the same features. There's this kind of curved feature in both of the images. You notice a few things about the James Webb image. One, it is kind of clearer and crisper. It's a bigger telescope with a bigger mirror. Sure, it gives clearer, crisper images. But don't forget, the Hubble Space Telescope is mostly a visible light instrument. It has an ultraviolet camera. It can see a little bit into the infrared. But the pictures you see from the Hubble are mostly visible light images. The pictures that you see from the James Webb are almost entirely infrared light. It sees a little bit into the red, but when you see a picture from the James Webb, that is an infrared picture that's been translated into visible light so that you can see it with your eyeballs. What that means is when we look at, say, this region of the Hubble Space Telescope, all we see is this gas that is blocking our view of the stars inside that nebula. When we see that same image with the James Webb, we see a lot of stars that we didn't see in this image. Why? Well, the James Webb has a bigger mirror, so it can see dimmer stars. There's that. But it can also see stars that are not yet giving off visible light. like a protostar, which is just forming out of that collapsing cloud of hydrogen gas. It is not yet fusing hydrogen into helium, so it's not thousands of degrees on its surface. It might only be hundreds of degrees on its surface. But it is giving off infrared light, and the infrared light can be picked up by the James Webb Telescope, so the James Webb Space Telescope can see through these clouds that are opaque to visible light and see infrared light being given off by stars that are just in the process of forming. One of the reasons that the James Webb was built is to look at very, very old galaxies way back just a few 100,000 years after the Big Bang, because the stars in those galaxies are just now forming and will be giving off not visible light, but infrared light. Not only that, their light is going to be highly redshifted because they're in galaxies that are moving away from us very, very fast. So the James Webb has the potential to tell us more about stars in the process of forming, as opposed to stars that are already fusing, like this one, already fusing hydrogen and helium and giving off visible light. We do have infrared telescopes before the James Webb Space Telescope, and we do see not only these dense clouds of, I need a pointer, these dense clouds of hydrogen gas collapsing into these globules, but we see places where the star in the center, or the protostar in the center, is just now starting to glow, and we see this kind of disk shape that we associate with this collapsing and rotating disk. Here are some pictures from, I'm not sure what satellite this is from. This might be from IRIS, an infrared observatory, but pictures of these gas clouds taken with an infrared telescope, and in every one you can see the protostar in the center giving off infrared light, giving off heat as gravity compresses it to denser and denser and denser states and higher and higher and higher temperatures. So what gives us confidence that our general picture of planetary system formation is correct is we can actually see protostars in the process of forming before they're actually fusing hydrogen into helium. Again, here's a lovely infrared picture of the region in the center of one of these collapsing clouds of gas that is giving off infrared light, but not yet visible light. The other thing we should see, if this model, this image, this theory we have of how planetary systems form, in addition to the protostar forming inside this cloud of gas, we should see this disk of material rotating around a star that will clump into planets. We call that a protoplanetary disk, and it's part of the theory, it's part of the model. This is what should happen along the way as this gas cloud turns into a planetary system. Do we see that? Well, what should we see? We should see a flat disk of gas and dust. We should see planets starting to clump in that. This is just a painting. This is just an artist's conception. This is not a photograph of what our solar system might have looked like just as it was starting to form, just as the planets were starting to form and grow. What evidence do we have that this really happens? Here are some pictures of a relatively nearby star called Beta Pictoris. This one is taken with an infrared telescope. This one is taken with a visible light telescope. But it's taken with, you see this kind of pixelated blob here in the center. It's taken by blocking the light of the star so we can see the material around the star. Think of sometimes when you're driving into the sunset and the sun is down low and it's shining right in your face and it's hard to see the road. Sometimes you will hold your hand up while you drive so you can see the road and block out the light of the sun. Or sometimes at night when there's a bright street light or bright car headlights and you're trying to see something next to it, you hold up your hand to block out that bright light so you can see the other things nearby. This is exactly what the Hubble Space Telescope is doing here. It's putting a little thing to block the light of the star so that we can see what's around the star. And what do we see around the star? We see this faint disk. In this case, we happen to be looking almost exactly edge on. This disk of material surrounding this young star, Beta Pictoris, that looks kind of what we would expect a protoplanetary disk to look like. In fact, in the infrared, we actually see clumps in that disk. They're labeled here A, B, C, D, clump, 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 that may be planets actually starting to form and denser regions in that disk starting to clump together into what will be, in another 500 million billion years, will be a planetary system. So we see images of things that look like planetary systems forming. Here again, here's another picture of Beta Pictoris, that same star from the Hubble Space Telescope, where we've placed something in front of the light of the star to block it out. What we see is this disk of material, this flat plane of material orbiting around the star. So there is actual observational evidence that young stars that have just formed in the past few 100 million years are still surrounded by these disks of gas and dust that will clump together into planets. Oh, here it is in infrared. Again, you see very clearly, again, we've blocked out the star, and we see very clearly this disk of material orbiting around the star, just as we would expect from our model. So the general picture that stars form out of big gas clouds that spin and flatten, and the center collapses into a star, and the orbiting junk left over clumps together into planets, is fairly well established experimentally, observationally. We see all the stages of this process actually happening. How do we go from a cloud of gas and dust and ice crystals to planets? How does that process happen? We are learning a lot about this process, and I'll talk about why we're learning so much about this process in a minute. There's actually been a few new research articles come out that call into question some of our assumptions about how this process happens. So I don't want to say too much, because we're learning so much about this process that some of what I say could be obsolete in a year or two. Suffice it to say that the primary force on the large scale is gravity. Gravity takes any masses and pulls them together into clumps. There are also just forces of static electrical attraction at work. Think about what happens in your house if you've got hardwood floors and you don't sweep very often, or you don't vacuum your bedroom. If you've got hardwood floors, the dust underneath your bed clumps together just from static electricity into dust bunnies, these little loose clumps of dust. Nobody reached under your bed and took the dust and scooped it together into a ball like you make a snowball. It happened all by itself, just due to static electricity drawing dust grains together, and the bigger they get, the more static attraction they have for other little particles of dust, and they grow all by themselves into these little tumbleweeds of dust that can gather underneath your furniture if you've got hardwood floors. The same sort of thing happened in the early solar system. Little mineral grains stick together due to static electricity. The bigger they get, the more stuff can stick to them, until they start to have enough gravitational attraction to actually gravitationally pull other objects to stick to them, other little grains of dust, ice, and gas. Gravity is not making dust bunnies underneath your bed, because the gravity between two particles of dust on the floor is too small. But if you're in space with no friction, gravity can also help to pull these things together. So all of these objects are orbiting the sun, but they're all also interacting with one another and growing bigger and bigger and bigger over time. So we start with these kind of loose collections of dust grains, ice crystals, until they grow big enough to start to get to be the size of a baseball, the size of a sofa, the size of a house, the size of a building. And the bigger they get, the more material they interact with as they orbit the sun, and the more they scoop up other grains of dust and minerals and ice and gas. These embryonic planets are called planetesimals or protoplanets. We call them protoplanets once they get to be about the size of the moon. As they orbit the sun, growing bigger and bigger by clumping together, they will eventually sweep out they'll clear a space in their orbit where they've swept up all the stuff. And if they clear up all the stuff in their orbit, they'll stop growing because there's no more stuff for them to sweep up. You can imagine the process being sort of like making snowman. If you get like 3 or 4 inches of snow, you take a little snowball and you roll it around your yard, and it gets bigger and bigger and bigger as it rolls through the snow and gathers more material. But eventually, when you've rolled through the whole yard, there's no more material to gather up into your snowman. And so your snowman is limited in size by the amount of snow in your yard. Likewise, the size to which these planetesimals can roll up into a bigger and bigger and bigger objects is limited by how much stuff is in their orbit. So once they clean up their orbit, they stop growing. Computer simulations show that this happens when objects are about the size of the moon. When they're about the size of our moon, they've swept their orbit clean and they stop growing. Well, that's a problem for our computer models because Earth is bigger than the moon and Mars and Venus are bigger than the moon. So there has to be something that makes them keep growing bigger than that. So it's a little bit of a puzzle. How do planets keep growing once they, planetesimals keep growing once they sweep their orbit clean? We have some ideas for how this process works. And again, some of these pictures are changing in light of new evidence. If there is friction with the material in the disk, that will cause sort of a headwind. The planetesimal, as it's growing, as it's running into gas and dust, that will slow it down and that will cause its orbit to change. So this sort of headwind slowing down the planet will cause it to spiral into a different orbit. And as it spirals into a different orbit, there'll be more material for it to gather up. So that can allow planetesimals to grow a little bit more. There is a place in the solar system for any planetary system. If you have the sun in the center, as you get further and further and further away, it gets colder and colder and colder, and there's a line at which things that are gases in here, carbon dioxide and nitrogen, for example, will be ices out here. We know from looking at our planetary system that the terrestrial planets are made largely of rock and with gaseous atmospheres. But when you get out to the moons of Saturn and Jupiter and Uranus and Neptune, they're largely icy. And so there's a dividing line in the solar system where it's warmer and colder that's sometimes called the snow line. And it's the place at which, say if you've got carbon dioxide and nitrogen floating around here, it will be in gaseous form, and here it will be in the form of ice crystals. And that dividing line causes ice crystals to kind of accumulate at this point in this protoplanetary disk as all this stuff orbits around. This kind of wall of denser material inhibits the migration of material into the inner solar system, and material tends to pile up here. And at this point, larger planetary objects can grow because the material there is more dense. That happens to be almost exactly where in our solar system Jupiter is. Jupiter is located just outside of this imaginary line called the snow line, where gases and volatiles give way to ice crystals. And the denser material there in the snow line may be what allowed Jupiter to grow bigger and bigger and bigger and bigger. So it may be no coincidence that in our planetary system, our solar system, the largest planet lies just on the other side of the snow line, just on the other side of this barrier imposed by this denser material. And it may be common for large planets that are slowing down and migrating into the inner solar system get sort of stuck there at the snow line, and they grow bigger and bigger and bigger and bigger. The process of Jovian, of gas giant formation, is complicated, and I actually had a couple of slides in this presentation that I took out because I don't want to get too deep into the mechanics of some of the stuff, again, because some of it is changing right now. But let's take it as a given, as the snow line represents a natural barrier in the formation of planets in the solar system. But that raises a really interesting question, which is, do all planetary systems look like ours? Little rocky planets enclosed, big Jovian planets with icy moons out far away. Up until 1980 or so, the only planetary system we knew about was our solar system. So the only guidelines we had for constructing a model for how planetary systems form were our planetary system. 4 little terrestrial planets, asteroid belt, bunch of Jovian planets with a bunch of moons, Kuiper belt, Pluto, icy stuff out in the outside. That changed in the 90s and 2000s when we started discovering other planetary systems around other stars, some of which look very different from our own. For example, we have discovered planetary systems where, despite the snow line being a place where Jovian planets should get stuck and stop migrating to the inner solar system, we have found planetary systems with what's called hot Jupiters. Oh, I skipped something kind of important. We think, well, let's see. Remember I said that when growing protoplanets sweep out their orbit, they will stop growing and get stuck about the size of our moon, unless their orbit moves someplace different. What could cause a planet's orbit to move someplace different? Well, a great big planet like Jupiter that's always given it little gravitational yanks all the time can cause the orbits of these forming protoplanets to shift slightly over time and put them into places where they're sweeping up different material. So it might be that the presence of Jupiter at that particular point in our solar system, just outside of the orbit of the terrestrial planets, helped to yank around the orbits of the terrestrial planets and helped them to grow by moving them into regions of the solar nebula that had more material. So it could be that we owe our existence as a big terrestrial planet, big enough to hold on to an atmosphere and oceans which we need to be alive, that if it weren't for Jupiter living out there just on the other side of the snow line, these protoplanets that would become Mercury, Venus, Earth, and Mars would have gotten stuck at about the size of the moon. And if the Earth got stuck at about the size of the moon, we would not be here. The moon can't hold on to an atmosphere and an ocean. It doesn't have enough gravity. So if the history of our solar system was a little different, if Jupiter was not sitting out there beyond the orbit of Mars, these planets in the inner solar system might have frozen out at about the size of our moon and Mercury and never gotten any bigger. Is that luck? Is it common? Is it always going to happen that there's a Jovian planet just outside of where the terrestrial planets live? It looks like the answer to that is no. As I said, we have discovered a lot of other planetary systems. We now know of more than 1,000 planets. I think the number is up to 1,500, 1,800 planets around hundreds of other stars. Just in the past 2 decades, we have discovered hundreds of planetary systems that we did not know about 30 years ago. One of the things we find in some of those planetary systems is something called a hot Jupiter. Some of the earliest planets we discovered were planets with masses like Jupiter and Saturn, but orbits like Mercury. In other words, a Jupiter-sized planet orbiting around its sun just 30 million miles away from it, orbiting every 10, 12, 20 days. There's nothing like that in our solar system. There are no Jovian planets in close to the sun. We never even, when constructing our models of how planetary systems form, considered the possibility of a Jovian planet in close to the sun, because we don't see that in our planetary system, in our solar system. One of the pitfalls of trying to create a theory when you've only got one data point is that theories have to be generalizable. They have to explain everything that can happen, and if you've only got one solar system to look at, you don't know what the possibilities are. So since year 2005 or so, we have discovered that some planetary systems are very different from ours, which means the dynamics of planetary system formation in other planetary systems could be very different from our own. There could be some planetary systems where the material is so dense that the barrier provided by the snow line doesn't keep the Jovian planets from migrating inward, or could have a density that's so low that the Jovian planet just passes right through the snow line as it's forming, sweeps up that material, and falls in closer and closer and closer and closer to the star. We don't think, at least I don't think, not last time I checked, we don't think a Jovian planet can form in here where Mercury lives in our solar system. It's too hot. The hydrogen would all evaporate before the atmosphere clumped together. We think that in these hot Jupiters, these Jovian planets formed out in the outside part of the solar system and gradually migrated inward. By the way, that would have spelled doomsday for any Mercury or Venus or Mars-like orbit or Mars-like planet that was forming in this solar system, in this we call planets around other stars exoplanets. So in this other solar system with a hot Jupiter, there could be no Mercury or Venus or Earth. They would have gotten swallowed up by the hot Jupiter as it made its way in from the outer solar system to the inner solar system. So what that means is that our contemporary post-2020 models of planetary system formation have to account not just for our solar system where we live, but have to account for the thousands of other planets and hundreds of other planetary systems that we have observed in the past 2 decades. So this is a very fast changing subfield within the field of astronomy, understanding how planetary systems form. The basic general overall picture I've given you is probably never going to change, but the specific details of how and where terrestrial planets form and clump up and what the influence of the Jovian planets is and where Jovian planets form is all still being worked out. I plan to post an article, and maybe if I can find a video associated with that article, about some of the ways that our picture of planetary system formation and planet formation are changing. And some things that we thought were right for a long time that are now probably not quite right. So I will add some of that material up to Canvas for you guys to look over, and I will leave it to more contemporary, up-to-the-minute news sites to give you some of the newest ideas about planetary formation based on our newest discoveries. And what we'll talk about next is how do we discover planets around other stars? How did we discover that there are thousands of planets around hundreds of other stars? And so we'll talk about that process, the tools that we use to discover those planetary systems in another video.